All right. Well, good morning. Happy Friday. Um, bit of I don't know, a little bit of a different lecture today. Um, I wanted to spend a little bit of time reviewing statistical inference. I know as a kind of a prerequisite for the class, everybody has taken an introductory statistics course or maybe AP statistics or something along those lines. And so I'm not going to be presenting anything new per se, but I do want to make sure we're all on the same page regarding hypothesis tests, p-values, confidence intervals, statistical inference, things like that. Just because we're going to move forward and we're going to do randomization tests, we're going to do bootstrap, and we'll run hypothesis testing in those contexts, and it's not going to make any sense unless we have a good solid understanding of statistical inference in the first place. So yeah, we'll just kind of blitz through this stack of slides I've got, covering introductory statistics, and so we'll just start off kind of at the beginning. So I'm going to try to, if you took Stats 10, it was 10 weeks long. I'm going to try to compress all of that in 50 minutes here, so we'll see. All right, so we often start off with descriptions of the center, and so we have like the mean and the median, and I guess we know how to find the mean, we know how to find the median, and certainly it's even easier on the computer. You just type in mean, you just type in median, and it gets you these numbers. But I don't know, I'm always surprised when students have a hard time kind of explaining these things. And so the reason why these are measures of center is that the median and mean, they both balance things. The median balances the number of data points on each side so that you have the same number of data points below as you do above. It's the 50th percentile, so half are below, half are above, so it balances the number. Whereas the mean balances the deviations, or the distances from the center on each side. So wherever the mean is, and you measure kind of the distance from the mean balances those things into account. All right, and so because the mean takes into account basically the magnitude, the size of these deviations, it's going to be affected by skew and outliers. So if you have something, way outlier high, the mean gets pulled in that direction because it's trying to balance out the distances or those deviations. Okay. So in skewed distributions, the mean is pulled towards the skew, whereas the median is not affected by those really big distances and is often kind of the preferred measure for when you have heavily skewed data. But I mean, certainly in some cases, you want to have something that reflects that skew. Anyway, here's just a little diagram. Let's say you have these numbers 1, 2, 3, 4, 10, and 10. Okay. 6 data points, the median balances the number of data points. So you're going to have 3 below the median, that's this blue line, 3 below the median and 3 values above the median. Okay, whereas the mean balances the deviations. The mean is in red at 5, and so if you say, all right, what's the deviations above 5? 10 is plus 5 and 10 is plus 5. You have 2 of those things, so you have things add up to 10 on the right hand side, and then you look at the deviations below, and you have 1, 2, 3, 4. That adds up to 10, so you're balancing out the deviations. Okay, so they're both ways to balance out the data. It's just, what are you balancing? And one is you're balancing the number, and the other is you're balancing these deviations. Okay, the other things that we have are ways to measure spread. Okay, spread is how far out the values are spread around the mean. And so, the variance and standard deviation measure how far values are spread around the mean. We have other measures of center, range and IQR and things like that. But this one, if you have small variance, small standard deviation, that means the values are pretty close to the mean, not a lot of spread. So you can think of like the ages of, students in a second grade classroom, like if you pick one grade in elementary school, what are the ages? And pretty much everyone's like the same age, right? 7 years old, 8 years old in second grade, not a lot of spread, okay? Whereas large variance or large standard deviation means the values are a lot more spread out. So if you think of, going to the waiting room at the DMV, where you have, teenagers and adults and seniors and babies and children, and you got all kinds of ages in there, you're going to have, large variance or large spread there, okay? The formula for the variance is basically, you can think of it as the average squared distances, okay? So, squared distances from the mean. So you take each value and you subtract off the mean to get the distance from the mean, and then you square each distance, right? And then if you take the average of those square distances, that's the population variance, if you happen to know what the true mean of the population is, okay? But generally you don't know the population mean, so you use your sample mean. And when you do this, to kind of correct for using x bar instead of mu, we divide by n minus 1. That's Bessel's correction. This is this is kind of like our average square distance from the mean, but kind of adjusted and corrected. And this thing is known as Bessel's correction. You guys cover this in 100b? Is that where you talk about why it's n minus 1 and not n? And it's like, again, if you knew the population mean mu, you would just divide by n. You would get the average square distance from the mean. But because you don't and you're using x bar, the usage of x bar always is going to kind of be biased towards being the center of your particular data set. So it's always going to underestimate the mean, and it turns out the way you fix for that is you divide by n minus 1. That's what we have there. Okay, lots of different probability distributions, but probably the most important one, at least in intro stats, is the normal distribution. It's unimodal, symmetric, looks like this. Most of the values are close to the center, okay? With the mean being at 0, this would be our standard normal. And the empirical rule says, yeah, you know what? 68, 95, 99.7 are within 1, 2, and 3 standard deviations. 95% are within, more precisely 1.96, but just kind of nice even numbers. If you go plus or minus 1 standard deviation, you get, just a touch over two-thirds, 68%. 2 standard deviations, 95. And then within 3, you get almost everything. And looking at our diagram, there's only just this tiny little piece beyond -3 and a tiny little piece above -3. We get almost everything, 99.7% within plus or minus 3 standard deviations. All right. So as far as statistical inference, it's all based around the idea of trying to make inferences about the population based on a sample of data, okay? So any kind of study or research question that we have, the population is everybody, right? The complete set of individuals or units relevant to a research question. The problem is that the population is just too big. We can't look at everybody in the population. So what we have to do is we have to collect a sample or a subset from the population. Based on that sample, we make inferences about the population. So just an example research question, you might wonder, is some new experimental drug, XYZ, is that effective at treating some disease? I just call it disease JKL, right? The population would be everybody, all individuals with disease JKL. We have no way to identify everybody, okay? Because, one is, how big this population is. It could be way too big. And then also, just practically speaking, medical records are private, so we can't know who has, you interact with somebody, you have no idea whether they have any kind of particular health condition or disease or anything like that. So, there's no way for us to identify all of these individuals. Even if you were a hospital or whatever, you only have access to those particular patients and whatever, okay? Weird. Okay, let me... All right. And we work with a sample, which is going to be a subset of individuals, with that particular disease. Let me see. Okay. And ideally we get our sample via random sampling, but there's lots of different sampling methods. Is sampling methods an elective option for you guys? No? Okay. It's actually like if you were to work for, say, like the Census Bureau and things like that, or Pew Research or any of these kind of public opinion things, like the topic of sampling, like the practical things of sampling are actually really, really hard to get like a good sample. Like in all of our textbooks and all the lectures and stuff, we just say, hey, we got this via random sample, just because mathematically it's convenient to say random sample. But like on a practical level, like if I just said get a random sample of students at UCLA, it's like impossible. Okay, like you could get you would have to work with the registrar's office, and then you have to define like who is a student. You have to like clearly define. Now, are we talking about full-time students? If a student just takes one class during the summer, are they a student? Should they be part of your population? You have to like clearly define what your population is. You would need access to all of those kind of student records. And then you have to hunt down every single one of those. Like if you might be able to sample the list that way, but then you have to like, let's say you selected 200 people. You have to like hunt all of them down, and people don't even respond to emails and stuff. And so it's even something where you have a list of everybody, it's really hard. And then if you're working at anything bigger than that, like Los Angeles County or the city of Los Angeles, like nobody has the sampling frame where you have a list of everybody. But anyway, all to say, random samples actually really kind of hard. But anyway, this is my terrible diagram. This thing, which kind of looks like a potato, but is supposed to represent the population. Okay, this is everybody. Okay, and again, the issue is that it's too big for direct study. So what we do is we select individuals. Okay, that's these little dots here, and they become part of our sample. And we study that sample, and based on what we see in the sample, we make inferences or conclusions about the population. Okay. Now, random sampling, that's the method that we use because we can talk about mathematical properties of a random sample, and also random samples should produce a sample that is representative of the population, but there's no guarantee, okay, because it's random, right? Because it's random, just by chance, you could get a non-representative sample. You could get a sample that doesn't look like the population by random chance. And especially if you have a smaller sample, you're at risk of that. But mathematically, in the long run, there's no reason why a random sample shouldn't produce a representative population overall. But it's random, so who knows? Okay. When we take a random sample and compute a sample statistic, like the mean of a sample, that value is going to vary from one sample to another, okay? And so if you think about what are the different kinds of values of X bar that you can get across all of the different possible random samples out there, right? And so in there's going to be lots of them, okay? Lots of different possible random samples, and you're going to get different possible values of X bar. The distribution of all those different values, that's the sampling distribution. And if we're talking about the mean, it's the sampling distribution of the mean. Here, Okay, before I forget, let me give you your first view quiz answer today, which is the letter E. E as in elephant. E as in elephant. And we have the central limit theorem that says if your sample size is big enough, okay, then the sampling distribution, I don't know what's going on with these lights, then the sampling distribution of x bar is approximately normal, okay? The mean is going to be mu, which is the true population mean, and the standard deviation is sigma, the standard deviation of the population divided by the square root of n, okay? And then the standard deviation of your sampling distribution is called the standard error of the mean. Large enough is kind of a weird thing. Usually we say, hey, n greater than or equal to 30 is big enough. But of course, if the population is normally distributed, and you know that, then small samples are fine. You could, central limit theorem applies, with samples of size 2, okay? Or I guess technically even 1 if the population is normally distributed. And then things that are skewed, like highly skewed, you might need a really much bigger sample, or we would recommend, taking the log or doing some kind of power transformation. But most day-to-day things, a sample size of 30 or more is going to be big enough. Okay, we can kind of simulate a sampling distribution. Okay, and so we start off with some arbitrary population. Okay, and I think I did just a standard normal population where the mean is 0 and the standard deviation is 1, but we could specify any kind of population we want. It doesn't have to be normal. It doesn't have to have a certain, you just have to specify some kind of population. And then what we're going to do is we're going to draw a random sample from that population, and we would calculate the mean of that sample, and then we're going to repeat that. We're going to draw another random sample from the population and calculate the mean, and you do that over and over and over again. You keep track of every single sample mean that you get, and then you look at the distribution of the sample means, because that's the idea of the sampling distribution. What are the different kind of possible values can you get for the sample mean, or in that matter, any other sample statistic. So here is just a random sample. I drew this from the normal distribution. This is the rug plot. So I got negative 2.21. Negative 0.84, negative 0.82, so these are two little red lines right next to each other, negative 0.63 and negative 0.62, again, two little lines right next to each other, negative 0.31, negative 0.04, and then 0.18, 0.33, 0.39, 0.49, whatever, okay? So on and so forth. These are the different dots, and the mean of those values, I think I got 16 values here. The mean is 0.092. Here is another random sample, and when I take this random sample, you can see the rug plot change. We've got the same population, but my random sample changes. And the mean of my sample is just ever so slightly different. You can barely see it shift, going from 0.092, so right there, to 0.096, okay? So just a tiny shift. Here's another one. That one is over here, and the mean ends up being negative 0.197. And this one, by random chance, we got some values that were quite high, and not a whole lot of negative values, and so its mean is 0.426. And these are just, I could just kind of repeat the process over and over and over again, and then that's what I do. So I just say, hey, let's do 10,000 of these things, all right? And I write just a very, very simple loop, okay? And I just say, hey, do this 10,000 times. Each time, take a random sample from the normal distribution of 16 values, and that will be your sample. Calculate the mean of that random sample, and then store that in our kind of vector of sample means. And so after I do this 10,000 times and I say, hey, what is the mean of all of the different sample means that I get something very, very close to the population mean of 0. I get negative 0.0015, so really close to that. And then the standard deviation, the population standard deviation is 1, and our sampling distribution should have a standard deviation of 1 over the square root of 16, or 1/4, and we do get something very close to that, 0.25, so pretty close to 25%, just off by less than 1%, less than 1 percentage point there. Okay. And here is a histogram of the different sample means that we have. Okay, this is my, simulated sampling distribution, and it looks very much like the normal distribution, with a standard deviation of 0.25, around 95%, between 0.5 and negative 0.5, and then I can do a QQ plot, and we see, yep, that lines up pretty much almost a perfect straight line, so it follows the normal distribution quite closely, and we're satisfied with that. Okay, so the key insight here now, with this, now that we have a sampling distribution, is we can start performing inference and start making conclusions about the population based on a sample. Okay, so assuming our sample is large enough, the central limit theorem says that the mean of a random sample comes from the normal distribution centered at mu. Okay, and the standard deviation, sigma over square root of n, which is what we call the standard error, and that quantity, the standard error, shrinks as the sample size increases. Okay, empirical rule also tells us that 95% of the time, when you draw a random value from the normal distribution, it's going to be within 2 standard deviations of the mean. Okay, so the insight is this: when I draw a random sample, there's going to be a 95% probability that the mean of this random sample is going to be within 2 standard deviations of the population mean. Okay, all right, and so because of that, okay, when we observe a random sample with mean x bar, we can be 95% confident that the population mean mu is within 2 standard deviations of x bar. Okay, because the thing is, if I know the mean and I draw a random sample, 95% of the time, my random sample will have a mean within 2 standard deviations. And so the flip side is that if I have a sample with mean x bar, I can be 95% confident that the population mean is within 2 standard deviations of x bar. Okay, and so that forms the basis of the confidence interval. The problem is that we don't know the exact standard deviation of this sampling distribution. We don't know what sigma is, sigma divided by the square root of n. So what do? We approximate it, we estimate it using the standard deviation of my sample. I use s divided by the square root of n instead of sigma. Okay, but now that brings in extra uncertainty, and so mathematically what we do is we correct for it using the t distribution instead of the normal distribution. And so instead of using 1.96, we use a slightly bigger number to kind of offset for our uncertainty. And that, you have the degrees of freedom, and so lower degrees of freedom, you have to offset more. If you have infinity degrees of freedom, t distribution and normal distribution are the same, so you end up using 1.96. But anyway, this is your confidence interval formula. You have the mean of your sample plus or minus some number times the standard error. We call this the margin of error here. Okay. Let's say we just making up something. Let's say I make a 95% confidence interval for the population mean mu based on our sample, and let's say our confidence interval is 12.2 to 16.8. Okay. The correct interpretation is something along these lines. Based on the data we collected, we are 95% confident that the mean of the population is between 12.2 and 16.8. Okay, 95% confident about that, right? Other things you can say is that if you repeat our sampling procedure a whole bunch of times, and produce a confidence interval, okay, about 95% of those intervals would contain the true population mean mu, okay? Now for this one particular sample, our best estimate of mu lies between 12.2 and 16.8, okay? So that just applies to this one particular sample that we have, okay? The 95%, as far as 95% confidence interval, refers to the long run frequency of capturing the population mean mu in repeated sampling, not, okay? It is not the probability of mu being in any one particular calculated interval, okay? It would be wrong to say 95% probability that mu is in here. We just have to say I'm 95% confident that mu is in here, okay? So the reason why, all right, so these are incorrect interpretations, okay? One thing is to say there's a 95% probability that mu is between 12.2 and 16.8, okay? The reason why that's incorrect is because, at least from a frequentist statistics, frequentist probability view, that unknown value of the population mean mu, it's a fixed value, okay? It's fixed, it's unknown to us, but it's not a random variable. And so it is incorrect to talk about probability. It would be akin to say, before I flip a coin, I could say, hey, what is the probability that the coin is going to land heads? Okay, and it is correct to say the probability that the coin will land heads is 0.5. That there's uncertainty. There's going to be a 50% probability that the coin will land heads. That is correct. Okay. However, like once I flip the coin and it lands, okay, if I ask the question, what is the probability that the coin landed heads? From a frequentist perspective, that is a nonsense question. Okay. There is no probability associated with the coin. It either landed heads or it didn't land heads, okay? To say there's a 50% probability that it landed heads is nonsense. There's no probability anymore. It is a fact. It is determined. So, but you don't know how it landed. It's unknown. The outcome is unknown to you. So what you have to say instead is, I am 50% confident that it landed heads, 50% confident. And so it's a subtle difference, but talking about probability for things that are fixed and not subject to randomness is, at least from a frequentist perspective, is nonsense. So it is nonsense to say there's a 50% probability that a coin has landed heads, because it either did or didn't. And it's also nonsense to say there's a 95% probability that mu is between this number and this number. Either it's in that interval or it's not, okay? It's unknown to us. We're 95% confident that it's between here and here, but in reality, it's some fixed number. There's no randomness, so it's either in there or it's not, okay? Other things that are wrong to say about a confidence interval, 95% of the data lie between 12.2 and 16.8, or the next sample mean is 95% likely to fall between 12.2 and 16.8, okay? Confidence intervals refer to the mean of the population, not individual observations, and it's always specific to the population mean, not anything about future samples or the means of future samples. Okay. The other bit of statistical inference probably covered in your introductory statistics class is hypothesis testing, and so I want to talk about that. Let me give you your second view quiz answer, which is the letter C. C as in cat, okay? C as in cat. All right, and so in hypothesis testing, we start with a claim about a parameter, commonly the population mean, but really you can make a hypothesis test about any population parameter, the proportion in a population, the variance of a population, whatever. And we ask, if this claim were true, if this null hypothesis claim were true, how likely, okay, is it that we would see the data that we have, data like ours, or something more extreme, just by chance, okay? And so the hypothesis test sets up a framework for us to kind of think about our data, what we would expect, and what we actually do see, and how to kind of compare them. And so we start off with our null hypothesis. This is the claim about the population. typically a statement claiming that there's no effect or no difference. And, oftentimes if we're trying to show that there is a difference, we're like hoping to reject that null hypothesis, okay? The alternative, which we write with H1 or HA, that's going to be, the statement that we might suspect might be true instead, okay? We calculate a test statistic, okay, like a t-score or a z-score or, chi-squared value or whatever it might be, f, okay? And that's going to be some kind of measure that compares the observed data that we have to what we would expect if the null hypothesis were true, okay? So we have a way to kind of compare what we have versus what we expect. We get the p-value, okay? And that's the probability of getting a test statistic as extreme or more extreme than ours if the null hypothesis were true. And then we make a decision. If that resulting p-value is less than a chosen significance level, we often use 5%, okay? Then we say the result is statistically significant, and we would reject the null hypothesis. I want to kind of just dive into this just a touch more, okay? So, for example, one of the most early hypothesis tests that you've learned is the two-sample t-test. We want to test whether two independent populations have the same mean. So your null hypothesis is that population 1 and population 2 have, means mu1 and mu2, and those two population means mu1 and mu2 are equal to each other, okay? Your test statistic, okay, compares the difference that you observed, your sample mean, x bar 1 and x bar 2, okay? We measure that difference and we compare it to the standard error, okay? Get a ratio. And then we calculate the p-value. What's the probability of observing a difference as large as or larger than whatever we got, x bar 1 minus x bar 2, whatever difference we got, if the null hypothesis were true? If the null hypothesis were true, we would expect this difference to be around 0 or close to 0 because mu1 and mu2 are equal to each other. Now, there's randomness, so they might not necessarily be exactly 0, but we would expect that difference to be small, okay? Anyway, you calculate your p-value and you say, hey, what's the probability of getting whatever we actually have, okay? If the p-value is small, then the observed difference that we actually do have is unlikely to have arisen from chance alone, and so we conclude that the reason why they're different is because the population means are different, okay? So the p-value, it's important. The p-value is not the probability that the null hypothesis is true, okay? The p-value is defined as the probability that if we assume the null hypothesis is true, okay, the probability of getting our data at least as extreme as that which we observed, okay? The probability of getting our data is something more unusual if you assume that the null hypothesis is true, okay? Extreme here depends on the context. Typically, it just means farther from what we would expect, okay, under the null hypothesis. Depending on your alternative, extreme might be, that number or greater, or extreme might be that number or less, or that number or more distant from, whatever the mean is, 0 or something, okay? A small p-value means the data that we have is unlikely if the null hypothesis were true, and therefore the fact that we actually do have it means we would reject the null. Whereas a large p-value means the data that we have isn't too surprising if the null hypothesis were true, and we failed to reject the null hypothesis. Again, but failing to reject is not the same thing as accepting the null hypothesis, okay? Failing to reject the null hypothesis doesn't prove the null hypothesis is true. It just means that we don't have enough evidence to rule it out, okay? A small p-values signal rare events under the null hypothesis, okay? If the null hypothesis really were correct, if it really were true, then most of the time we'd expect our observed statistic, our data or whatever, to lie within a typical range. So if we're talking about mu1 minus mu2, or mu1 equaling mu2, we would expect our difference between x bar 1 and x bar 2 to be close to having a zero difference, okay? Other situations, there's a certain kind of range of values that you would expect your sample statistic to be, okay? But if you do your calculations and you end up with a small p-value, okay, that indicates that the data that we actually have would be quite rare, okay? That would happen only a small fraction of the time if the null hypothesis were in fact correct, okay? So an analogy is, think about rolling a die. Your null hypothesis is that the die is fair. And let's say you roll the die 10 times and you get the number 6 8 times out of 10, okay? And you calculate the p-value. You say, hey, what's the probability of getting our result of 8 or more 6s and 10 rolls if the die is actually fair, okay? The probability of something like that happening with a fair die is really, really, really unusual, right? It's on the order of like 10 to the minus 5 that just by random chance you happen to roll the number 6 8 times out of 10 rolls, okay? Therefore, because such an outcome is unlikely under, assuming that you have a fair die, the fact that we got this result tells us that our assumption is incorrect, right? And we say the reason why I'm getting 8 6s out of 10 dice rolls is because I'm going to reject the null hypothesis. The die isn't fair. Something else is going on. That's how you explain the data that we have, okay? Now, is it possible that the die actually is fair and we just got this really crazy outcome? It's also possible, but that's just really surprising because the probability of something like that happening is so small. So we just say, hey, you know what? I don't think I was one of the lucky 1 in 100,000 people where this kind of result happens. Rather, the reason why I'm getting this is because my die is fair. Okay, so yeah. So why do we reject the null if the p-value is small? A very low p-value basically means if the null hypothesis were true, the data we have would be very unlikely or surprising, okay? So, we have enough evidence to conclude that our observed data don't look like what should happen if the null hypothesis were true, okay? We have an idea of things that typically happen if the null hypothesis were true. Our observed data doesn't look like that. And so rather than attributing our observation to a wildly rare event, we conclude that the null hypothesis isn't true, okay? That's why we're rejecting it. The way we make our decisions is we compare our p-value to some cutoff, okay? We call that our significance level, 5%. So if the p-value is less than alpha, we reject the null and we say our result is statistically significant, okay? Meanwhile, if the p-value is greater than alpha, we say the data could reasonably occur under the null hypothesis, and so we don't reject the null, okay? Now, again, we don't claim that the null hypothesis is true, just that there's not enough strong evidence. There isn't strong enough evidence to reject it, okay? It just, it doesn't, you flip a coin 20 times, you're expecting 10 heads. Let's say you get 12 heads out of 20 flips, okay? You're not going to reject the null hypothesis. You're not going to suddenly assume that your coin is unfair, okay? But it doesn't also prove that the coin is fair, right? Maybe you're getting 12 heads out of 20 flips because the coin actually is unfair and it's supposed to land heads 60% of the time, okay? But it's just that getting 12 heads out of 20 flips, it doesn't look all that different from what a fair coin could produce. So we have no reason to doubt that it's a fair coin, but at the same time, it doesn't prove that it's a fair coin either, okay? Our significance level, alpha, that's also the probability of making a type 1 error. Type 1 error is a false positive, okay? That means we rejected the null when the null hypothesis is true, okay? So, false alarm or false positive. So that would be something like you come to the conclusion that a new drug works when in reality it doesn't work, okay? We have control over alpha, and so when we pick alpha of 5%, it says we're willing to tolerate making type 1 error 5% of the time, okay? Type 2 error is determined, is your probability beta. Probability of a type 2 error is beta. That's the probability of failing to reject the null when the null is actually false, okay? So this is a missed detection or a false negative, and so an example of that would be concluding a new drug doesn't work when in actuality it actually does work, okay? And then power is the probability of correctly rejecting the null when the null is false, okay? High power means you have a better chance of detecting a true effect. We often aim for a power of around 80% or a type 2 error of 20% or less, okay? This is kind of a table. If the true result is that the null hypothesis is true, what we want to do is fail to reject. That's the correct outcome, okay? Whereas if we reject the null and the null hypothesis is true, that's a type 1 error, okay? If the true outcome is that the null hypothesis is false, rejecting the null hypothesis is the correct decision. That's power. And if we fail to reject it, that's type 2 error, okay? We have, these t-tests and whatever, these fall under the classifications of parametric tests, okay? And they rely on assumptions of normality, and mathematically we justify them using the central limit theorem. We have other kinds of tests like randomization tests and bootstrap-based tests and things like that, and that actually uses the process of random assignment and randomization to generate your reference or sampling distribution for the test statistic. And that's what we're going to be exploring next week. Okay, so next week, today is just kind of a review of all of this inference and parameter-based stuff. Next week we'll get into the computational statistics part of this. Okay, we want to so randomization tests require exchangeability, and that is the idea that under the null hypothesis, labels or treatments could be swapped without changing the distribution of outcomes. Okay, so that's what we are going to take a look at. Okay, but before we do that, I want to just do a quick review on data collection, and this will be the last few slides. And let me give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear. B. Okay. How we obtain our data matters. Okay. Whether we got the data via random sampling or we did an experiment with random assignment is going to be important regarding whether we can make conclusions that kind of generalize to broader populations, or whether we can make cause and effect relationships. Okay, so here are 4 scenarios for some hypothetical experiment where we give vitamin C, or we ask about the relationship between vitamin C and reducing, canker sores in the mouth. Okay. So one is, let's say we do an observational study and we don't have a random sample. Okay. So we have patients with appointments in the first 2 weeks of December are asked about their vitamin C use, and we collect our data. We split them into those who take vitamin C takers versus non-takers, and then the result is that, let's say we do our analysis, those who took vitamin C had fewer canker sores than non-takers. Okay. Now the problem here is this group isn't a random sample. Okay, we just have patients with appointments in the first 2 weeks of December. It isn't a random sample of any larger population, so we're not going to be able to generalize our results to any kind of bigger group. All right. Also, no random assignment or for the treatment. It's a purely observational study, so we can't infer any kind of cause and effect relationship, just that there's an association, okay? Let's say we do use random assignment, but we have a non-random sample, okay? So if we have the same kind of non-random group of patients, but now we randomly assign some of them to take vitamin C, and we tell some of them don't take vitamin C. Okay, again, same results. Those who took the vitamin C have fewer canker sores than non-takers, okay? This isn't a random sample, so again, we can't generalize beyond this group, but the random assignment does allow us to make causal inference for this group. We could say the differences between the canker sores can be attributed to the vitamin C usage, okay? Assuming the other kind of confounders or at least controlled are also randomized. So we can say because we randomly assign who's going to take vitamin C and who's not, we can draw a cause and effect conclusion, okay? If we have a random sample and it's an observational study, all right, so we get a random sample of patients selected from the town, we observe who already takes vitamin C and those who don't, okay? Again, because it's a random sample, we can generalize to the population, which would be, I guess, all dental patients in the town, because I guess the study is being conducted at the dentist's office or something. So we do have a random sample, and we can generalize to the population, again, but it's observational, so we can't draw cause and effect conclusions, okay? There could be other confounding variables correlated to vitamin C usage. All right, and then finally we have the random sample and random assignment, okay? Sample is random, so we can generalize. Assignment is random, so we can draw cause and effect conclusions. And beyond the town's dental patients, generalization depends on whether this population is representative of the larger group. But here we can do both, generalize and make cause and effect conclusions, okay? Now, this scenario 4 of having a random sample with random assignment is like our ideal standard, but it is an unrealistic situation, okay? Achieving true random sampling and true random assignment is like a rare thing, okay? Experiments either rely on volunteers and convenient samples, so you're not going to get random sampling, okay? And random assignment can yield kind of valid cause and effect conclusions, but how do you generalize to the greater population? That's a lot harder. So when you do an experiment, oftentimes you're hoping somebody else is able to reproduce your results. They conduct the same experiment again with a different population, and you're hoping that your sample produced this result. Somebody else does it with a different sample, and they produce the same results. And then you're hoping, okay, well now we're getting something like different slices of the population, so we're hoping to generalize to the greater population. Okay, and then this is just kind of a summary of all of the things we've covered. Just kind of a lot, just trying to fit all of intro stats into one lecture. But how we're going to kind of move forward, and a lot of these ideas that apply to hypothesis testing will carry forward when we do our randomization and bootstrap-based hypothesis testing. So we'll end here for today. Have a great weekend. We'll see you next week, and we'll see you then.